We are on chapter 10, section 7, last one. So we know enzymes are amazing, amazing things that help us to speed up our chemical reactions in our bodies so that we can actually function. But there are lots of different things that can affect enzyme activity. And so what we're going to do today is we're going to talk about those different things that will affect our enzyme activity. One of them is substrate concentration, right? So the very first thing that has to happen in an enzyme catalyzed reaction is that we have to form that enzyme substrate complex. And the less substrate you have, the harder it is to make that enzyme substrate complex. So if our amount of enzyme remains unchanged, if we increase the substrate concentration, then we can actually make that reaction happen faster up to a certain point. And that point is the saturation point. So the enzyme is completely saturated with substrate, and even if you added more substrate, you couldn't go any faster. And so that's that steady state level, right? It'll continue. We'll add more substrate, add more substrate, add more substrate, and we'll look at the rate of the reaction. And the rate of the reaction will speed up until we just can't add anymore. The more substrate you add, then nothing happens. And you get to this steady state point, right? And so you get to that saturation point, and no matter how much more substrate you add, won't change it. But there's a big range where it will. So after that maximum activity, right, we get to steady state conditions. And at steady state conditions, our substrate's being converted to product as efficiently as possible. So we say that our analogy is that our enzymes are workers, right? And workers require tools to do their job, and they require parts. So here we have 3 workers, and they are making bicycles, right? So they have all the parts, and they have all the tools. The tools are like our cofactors and our coenzymes that we require in order to make it happen. But each worker only needs one set of tools, right? But however many parts you have, that's how many products you can make. So if you run out of parts, you can't make any more bicycles. But there gets to be a point where the workers, no matter how many parts they have, they can only make so many bicycles. So you have to look at substrate concentration as something that can affect the rates of reaction. The other ones are pH. So pH is really, really important, because if you change pH, we know this, you will change the protonation and deprotonation states of our side chains and of our N-terminus and our C-terminus of our proteins. And so if you change the pH, you are actually going to change the tertiary structure of your proteins. And remember, tertiary structure is what determines the active site of an enzyme. So if you change the tertiary structure, you're probably going to change the function. So when you do that, you have to be very, very careful. Usually what will happen is if you go outside of the normal pH range of your protein, of your enzyme, then it's going to cause a decrease in our enzyme activity, because whatever the protonation state of it was, it's no longer that. So it's not going to function as well. So in this analogy, right, if you remove active sites that are functional because you changed the pH, you have less enzymes that are able to do their function. And so now you can't make as many products, right? So that's kind of the same sort of deal. So if you look at different enzymes are functional at different pHs, right? Because not everything is the same inside of our bodies. We say physiological pH is about 7. And yeah, we got some enzymes that work optimally at about 7, things in the liver or things that are in basically all tissues. Those things do work at about 7, but we have different parts of our body where we have different pHs. Like think about the stomach. The stomach, you are making acid inside of your stomach. You have stomach acid. So you have really, really low pH. Whoa, oh my gosh, that's a pH of 2 inside of the stomach. Well, pepsin is an enzyme that works in that environment. And so it needs to be functional at very low pH. So if you raise the pH to 7, pepsin's not going to work. So each individual enzyme has its own optimal pH. Temperature can affect enzyme activity, right? Now, temperature is more tightly controlled inside the body. Basically, everything's at 37 degrees Celsius. And if you get above the optimal temperature, enzymes are not going to work because you're going to disrupt the attractive forces in the tertiary structure. And that's what we talked about in the last section, that temperature can change your tertiary structure. So at high temperatures, an enzyme will denature and turn into that spaghetti. At low temperature, enzyme activity is reduced. The enzyme's not denatured, but it is reduced because of the lack of the energy, right? Temperature is actually kinetic energy of molecules, how quickly they're moving. So if you decrease the temperature, then you have less kinetic energy, and then you have basically less energy available for the reaction to take place. And so either way is not good. So if the workers get too hot or they get too cold, they're not going to be able to produce their normal output. So one way that we take advantage of this is that we refrigerate all of our food, right? So why do we refrigerate our food? Well, there are bacteria present in everything. And it's the enzymes inside of the bacteria that are able to start to break down our food that we've cooked, and results in food spoilage. And so if you put it in the freezer or you put it in the refrigerator, right, either way, you're slowing that process down. And so that's one way to preserve things. You can also cook things, right? You can go the opposite direction. You can either make them cold or you can make them really hot. And so if you boil water, right, then you're going to denature the proteins inside of bacteria, and then you can drink the water. That's why we sterilize instruments before surgery. All kinds of things like that. So either or is going to help reduce things that you don't want to be there, like bacteria and viruses and things like that. Inhibitors can also affect enzyme activity. So inhibitors will work in a couple of different ways, but they basically prevent the active site from interacting with the substrate, so you don't make enzyme substrate complexes. There are some enzymes that cause some inhibitors, that cause our enzymes to have a temporary loss of activity, and there are some that are permanent changes. So if it's a permanent change, then it's basically a suicide inhibitor. The inhibitor is stuck with the enzyme, and so that's a permanent change. But more often than not, it's a reversible inhibition. And so the inhibitor causes the enzyme to lose catalytic activity, but if we take away the inhibitor, then the enzyme's functional again, right? So reversible inhibitors can either be competitive or they can be non-competitive. So let's talk about what that means. If you have a competitive inhibitor, that means that there's one active site, right? And there are two things that can fit in the active site. Either the substrate can bind in the active site or the inhibitor can bind in the active site, but only one can bind. So if your inhibitor is bound here, your substrate can't bind. So it's competing, both the inhibitor and the substrate are competing for the same site. So if the inhibitor is in place of the substrate, you're not going to form any product. But if we take away that inhibitor, if we remove it, now our substrate can bind and now we can make product. So that's why it's reversible, right? So if you want to reverse it, what do? You put in more substrate or you take out inhibitor. It's the same thing. So you can have non-competitive inhibitors. Non-competitive inhibitors typically bind at a site other than the enzyme's active site. So you have this triangular active site, right? And the substrate fits in it. That's great. But there's this secondary site, and the inhibitor will go in and bind in this secondary site. And when it binds in this secondary site, it changes the shape. So shape of the active site changes. And because of that, the substrate can't bind. So it induces a conformational change that makes that active site lose its shape. and it's distorted. And so it doesn't bind to substrate, so it doesn't make product. So in this case, right, for this to be reversible, the inhibitor has to be able to get out of that secondary site. So if it's reversible, the inhibitor can get out. If it's irreversible, right, then the inhibitor actually formed a covalent bond and it is like glued into that secondary site. It is stuck. And so regardless of whether it's in a secondary site or if it's in the primary site, doesn't matter. So it could be either one. So you could have a third possibility, right, where you have, here's your enzyme, but this enzyme has that little pocket, right? And so our inhibitor would go in, here's our inhibitor. Y'all pardon my drawing, right? And then what would you make? You would make something, whoop, it would change the active site. Now the active site looks different. And then we have this square inhibitor stuck inside of the enzyme, but it's covalently bound. So this will never revert back to its original shape. It's stuck because it's in, because it's covalently bound. It's in the pocket, whether it's in the primary active site or in that secondary site, doesn't matter. Reversible inhibitors permanently inactivate our enzymes. And so what if I added more substrate? Would that change? Nope, because you've basically eliminated the enzymes. You've basically said it's like they don't exist because this inhibitor is attached to it and will not let go, right? So if you have an irreversible inhibitor, adding more substrate isn't going to do much. But if you have something reversible where that inhibitor can let go and we can revert back to our original enzyme state, now we can bind substrate. So the more substrate I add, now the more active the enzyme becomes. Okay. So one example of this is antibiotics. This is how antibiotics work. Antibiotics are inhibitors for bacterial enzymes. So penicillin, our most common one, is an irreversible inhibitor. So it binds to the active site of the enzymes that bacteria use to synthesize their cell walls. So it doesn't actually kill bacteria. It actually prevents the bacteria from growing a cell wall. So they can't make more bacteria. And then your immune system takes care of the ones that are alive, right? So what else did I say? Okay, so yeah, without a proper cell wall for protection, bacteria don't survive. You can make no more new bacteria and your immune system goes in and kills the rest of them, right? It's really cool, really, really cool. And that is it. Yay, that's the end of the chapter. All right, have a good rest of your day. Oh, we got to do the questions. Oh, I'm crazy. Got to go do our question. All right, so my my undergraduate degree is actually in microbiology, which is why I get super excited about bacterial resistance and stuff like that. So then I forget we have to go and do problems. So how would the following changes affect enzyme activity for an enzyme whose optimal conditions are normal body temperature, that's 37 degrees Celsius, and physiological pH, so that's pH equal to 7. You need to know that. You need to know that. Raising the temperature from 37 to 60 degrees Celsius. So what would happen to our enzyme activity? Enzyme activity, up, down, or unchanged? Enzyme activity would go down because you're denaturing it. What if I lower the pH from 7.5 to 4? Wow, that's a huge change. Our enzyme activity would again go down. Okay. All right. The enzyme urease functions in the body to catalyze the formation of ammonia. So this is ammonia from, and carbon dioxide from urea, U-R-E-A, urea, as shown. Okay, so in the body, we're at 37 degrees, right? And it doesn't say anything about pH, so we don't have to worry about pH. So what happens if we add excess urea? Well, urea is a substrate. So if we increase a substrate, STR, oh my goodness, then we're going to make more product, right? So this is going to increase the rate of our reaction because now our enzyme has more substrate to work on, so it can make more product. Lower the temperature to 0 degrees Celsius. Ooh, so we are reducing the available energy available for the enzyme to work. So in this case, we are going to decrease the rate of the reaction. Let's see. Oh, did I do the wrong one? No, that's it. All right, that's it. Yay! Have a good rest of your day.